Hello everyone, now we have to discuss case 3, that is network which is having only dependent sources. Case 3, that is circuit is having only dependent sources. So, there is no independent sources in the network. Then, if there is no independent source in the network, then the network cannot be energized, right. So, dependent source means what? It should be dependent on other parameters, but here we do not have any independent sources, therefore, the network cannot be energized, therefore, it cannot produce any voltage or current. If there is no independent sources in a network, therefore, network cannot be energized, right. Therefore, then it cannot produce any voltage or current. It cannot produce any voltage or current. Therefore, VOC, which is equals to VTH 0. This is very important. If we have only dependent sources without independent sources, then the value of VTH is equals to 0. Then we are supposed to calculate RTH only, right. Only we have dependent sources, we do not have any independent sources, therefore, we have to calculate RTH only. For the network having dependent sources, right. Then how can we calculate RTH? We all know that to compute RTH, provide a DC driving voltage between open circuited terminals, then calculate RTH, right. So, because of DC driving voltage we have IDC, therefore, RTH is equals to VDC by IDC, that is it. So, the network which is having only dependent sources, for that networks we have to calculate only RTH, that is it. Let us discuss this problem. So, this is the network which is having only dependent sources. For this network we have to calculate RTH. So, here voltage controlled current source which is connected in parallel with a resistance. So, by using source transformation we can transform this into voltage. So, up to this is 100, we have 50. So, between these two we have 300 in series with, see, the arrow, that is like this. 300 into 0.1, that is 30 into V1, that is it, right. So, this is A, this is B, plus minus, this is V1. This is the modified circuit from the given circuit. Therefore, provide DC driving voltage between A and B. So, this is the circuit, minus plus, this is 30 V1, this is 350 ohms, this is 100 ohms, plus minus, this is V1, sorry, V1. So, between these two open circuit terminals, we have to provide VDC, right. This is A, this is B. So, due to this application of VDC, we have IDC. So, at this node, so by observation, by inspection, VDC is equals to V1, right. Therefore, IDC is entering, IDC leaving and leaving, that is it. VDC by 100 plus VDC plus 30 VDC by 350, that is it. So, from this 350, 100, 350, 700, 700 IDC is equals to 7 VDC plus 2 VDC plus 60 VDC. From this 700 IDC is equals to 69 VDC. So, from this VDC by IDC is equals to what? 700 by 69, which is equals to what? 10.46 ohms. Therefore, 10.14 I think, 10.14 ohms. Approximately it is 10 point something. Therefore, RTH is equals to 10.14. That is it. Answer is over. Simple. By providing DC driving voltage, we can calculate the value of RTH. The next problem is, so we have to calculate the RTH between this A and B. So, solution. This is A, this is B, this is 2 V naught, this is plus minus V naught, this is 1 ohm, this is 4 ohm, right. So, between these two, we have to provide VDC. So, due to the application of VDC, we have IDC. Okay. VDC, let us say this is V. Therefore, IDC is entering, this is entering, leaving, right. Therefore, IDC is equals to V. So, this current is entering towards this node, this 2 V naught plus 2 V naught. This is leaving, right, V minus V naught by 1, which is equals to V minus V naught by 1, that is it. So, this is one. At any case, we have to get the equation in terms of VDC and IDC. So, we have IDC, but we do not have VDC. So, in order to get VDC, we have to replace this V naught and V. Okay. So, that is the nodal equation at this node. Therefore, by inspection, see, this IDC is what? VDC minus V by 4, right? This IDC. IDC is equals to VDC minus V by 4. So, from this we can get V. 4 IDC is equals to VDC, V is equals to VDC minus 4 IDC, that is it. From this is 1, right? Like that we have to get V naught. So, in this equation V completed, then V naught. To get V naught, so see, this is 2 ohm. So, V, the current in this branch is what? V minus V naught by 2, which is equals to V naught by 2, right? V minus V naught by 2, which is equals to, so V minus V naught by 2, sorry 1, V minus V naught by 1, which is equals to V naught by 2, which is nothing but current in this branch, V naught by 2, that is it. Therefore, equation 1 implies, that is IDC plus 2 V naught. In place of this V minus V naught, we have to substitute V naught by 2, right? From this IDC is equals to what? V naught by 2 minus 2 V naught minus 3 V naught by 2, right? So, V naught by 2 minus 2 V naught minus 4 V naught, that is it. So, from this V naught is equal to what? Minus 2 IDC by 3, that is it. This is equation 2, that is it. Then substitute equation 1 and 2 in 1. Substitute 1 and 2 in 1. Therefore, IDC is what? As it is IDC plus 2 into V naught, 2 into minus 2 by 3 into IDC, which is equals to V minus V naught. V is nothing but VDC minus 4 IDC minus V naught plus 2 by 3 IDC, that is it, right? So, from this IDC minus 4 by 3 IDC is equals to minus 3 IDC. Where is VDC? So, this is VDC, right? So, VDC minus 12 10 by 3 IDC. From this 3 minus IDC by 3 which is equals to VDC, right. So, 9 IDC by 3 is nothing but VDC. So, from this VDC by IDC is equals to 3 ohms, 9 by 3. So, this is the Thevenin's resistance from this circuit. Let us discuss this problem. Simple. This is VDC, right? Because of this, we have IDC. That's it. That's it. That's it. And that's it. Clear. Therefore, IDC is equals to, this is VDC by 15, VDC by 15 plus VDC minus of minus plus 4 Vx by 10 plus 5, 15. From this 15, IDC is equals to 2 VDC plus 4 Vx. That is it. 2 VDC plus 4 Vx. But by inspection, this VDC plus 4 Vx by 15 equals, this is the value of current, which is equals to Vx by 5, right. So, from this 3, so VDC is equals to 4 Vx, Vx minus Vx. VDC is equals to, this is Vx, substitute this value of Vx into this. Therefore, 15 IDC, which is equals to 2 VDC plus 4 Vx. So, 4 into minus 4 VDC, right. 15 IDC is equals to minus 2 VDC. From this RTH, which is equals to VDC by, which is equals to minus 15 by 2. That is RTH is equals to minus 7.5 ohms. Is it possible to get negative value of Thevenin's resistance? No. Therefore, conceptually it is valid. Conceptually it is valid, but practically not valid. That is it. That is why I am considering this problem. So, we got negative value of resistance, but conceptually we will get that value, but practically we do not have that value. Let us discuss the advantages, limitations and applications of Thevenin's theorem. So, first one, advantages, it reduces complex circuit to a simple circuit, right. Then it greatly simplifies the circuit with lesser time. This theorem is used to determine the current in only particular branch. So, for these 3 points, here I am considering one example. For example, we have a voltage source, we have a current, again we have a voltage source and we have a branch, right. That is it, right. So, this is V1, this is V2, this is R1, R2, R3, R4, R5. This is the real circuit, right. So, what is the value of current through this branch? We have to calculate. So, if we compare mesh analysis and Thevenin's theorem, for example, we consider mesh analysis. So, in order to calculate the current through this branch by using mesh analysis, first we have to provide the loop currents, right. So, we have 1, 2, 3, 4 loops. So, in order to calculate the current in this branch, we have to provide 4 loop currents. So, by solving those, so here we have 4 loop, therefore, we are going to get 4 loop equations. So, by solving those 4 loop equations, we will get the current through this branch. It will take more time to calculate, right. So, for that we are introduced Thevenin's theorem. So, by using Thevenin's theorem, the current in this particular branch means what? For us, this is load, for this is A, this is B. Simply we have to remove this branch and calculate open circuit voltage, later calculate Thevenin's resistance, finally reconnect this branch as it is, calculate the current through that branch, that is it. So, the Thevenin circuit for this circuit is what? This is VTH, RTH, this is R3, right. At last we have to connect this R3, this is R3, this is RTH, this is VTH, then the current through this branch is nothing but I, that is it. So, it reduces complex circuit to a simple one, it greatly simplifies the circuit with lesser time. This theorem is used to determine the current in particular branch, that is it. This is the example for this. Coming to limitations, this theorem is not valid for non-linear and unilateral circuits. Clear. The Thevenin's equivalent has an IV characteristics only from the load point of view. So, for us this is load, right. For example, if we calculate the current through this branch, then the load for us is R5 branch. If we have to calculate the power delivered by this voltage source, for us this V2 is nothing but load. So, depends upon load requirement, we have to get the different IV characteristics. So, the Thevenin's equivalent has an IV characteristics only from which point of view? Only from load point of view, that is it. Next, the power dissipation by a Thevenin's equivalent circuit is not same as the power dissipation of real circuit. So, for example, this is the real circuit, this is the given circuit, from this we are going to get the Thevenin's equivalent circuit. So, what is the Thevenin's equivalent circuit? This is the Thevenin's equivalent circuit, right. For this real circuit, this is the Thevenin's equivalent circuit. Then the power dissipation by this Thevenin's equivalent circuit is not equals to the power dissipation by this real circuit, right. So, if we have a load, for example, the power dissipation in this circuit is equals to the 0, means the power absorbed, the power delivered are same in a loop circuit. But coming to the Thevenin's equivalent circuit, the power dissipation of this Thevenin's equivalent circuit is not same as that power dissipation in this real circuit. For example, if we have a voltage source, last as we have a discussion, right. For S2 branch, the power dissipation by that load is not always is equals to the power dissipation of this Thevenin's equivalent circuit. But coming to voltage source and current source as a load, the power dissipation of that load should be equals to the power dissipation of this Thevenin's equivalent circuit. If we have any doubt, go through the previous lecture. This is the third point. Coming to the applications, it is very useful for analyzing the power system and other circuits where one particular load resistance in the circuit and recalculation of circuit is essential with each trial value of load resistance. For what? To find voltage across it and to find current through it. So, in order to analyze the power system, we have to calculate the load resistance in trial and error method. So, for each and every time we have to get the load resistance by calculating different values of voltage across it and current through it. Next, source modeling and resistance calculation by using the Wheatstone bridge provide applications for Thevenin's theorem. These are the advantages, limitations and applications of Thevenin's theorem. This theorem is very most important compared to all other theorems.